write down so here x is a vector, and so x minus a, the norm of it can be written as root of x1. And then you will have to collect all of the partial derivatives, right? So what will happen is, we know that derivative of root of and then if you have x squared, then it is 1 by x squared x. Yeah, this is correct, but essentially the point is that when you have a sum of all of these together, and you have del of x1 minus a1 square plus x2 minus a2 square, you take derivative with respect to only partial derivative with respect to only the first element, you will have this thing will come down in the denominator 1 by 2 root of x. So this whole term itself, and then you will have twice of x1 minus a1, and essentially like that's what that thing is writing, because you can again replace this as the norm itself. Was that clear? I might have lost people in the derivation.
Does this apply for every norm or only the L2 norm?
This is, I've only shown for the L2 norm, and I think this derivation is also only for the L2 norm. Like, clearly we can see that for the LP norm, the derivative is going to be different. There are going to be other factors coming in. Like, there will be a square in the L3 norm. Square. But usually, since people are working only, like mostly they are working with the L2 norm, Euclidean norm, it's just helpful to remember this as an identity. So, okay. Quick exercise. So these problems are from Borup and Rohn, and so this basically is showing, say, the chain rule. This is a nice exercise. It's basically a way to apply things you're learning here. So, like, how do you prove that this is equal to this? Given the identities that you see on the board, it should be possible to derive it. First of all, let's read the question. So, like, you have a matrix A, and all of its entries are a function of some parameter alpha, right? And then you are taking the derivative of the inverse of that matrix. So you want to find all the partial derivatives of all the entries that will be in the inverse, and you are expressing it as this. So why is it that this formula is true? How would you derive it? This is useful because it can be used, it might be used in the course. So another hint that it can use this identity, which is on top. Any ideas, thoughts, like what might what might lead to a solution.
You can substitute in the above equation the B as A inverse.
Sorry?
In the first problem, the equation that's given, if you substitute B of alpha as A inverse,
Yeah.
then the left hand side becomes 0.
Yeah, that's true. That's the answer. Yeah. So if you put B alpha equals to, so B alpha can be anything, right? So if you put B alpha equal to A alpha inverse, this side becomes identity, which is independent of alpha. So this becomes 0, and then you will see that D of alpha A alpha inverse is equal to, you take this on the other side, D of alpha A alpha inverse, and then left multiply with A alpha inverse once again, and you get this. So there are some useful identities like these which can help you get a lot of the other algebra a lot of the time, like most of the time. Like you wouldn't have to actually get into, you wouldn't have to actually get into the index notation, and like you can, because it gets messy. Like it's easy to make mistakes. If you can work out on a higher level, it's much more easier. So yeah, so I would say that the ones that I have collected are kind of useful. So one was the chain rule, because chain rule you can, like if you can break it down into functions, like functions which you can easily differentiate, it's gonna, like even if it doesn't immediately appear as a composition of functions, you can always curry things, right? Like, and then just keep taking derivatives. And so at this point I have to introduce the matrix cookbook. So the matrix cookbook has, so there are, it basically has all of these things. So derivatives of determinant, inverse, matrices, etc., derivatives of traces. So if you're forgetting something, if you want to look it up, like this is one photo place. One thing to note though is that it does not use numerator layout, it uses a mixed layout. So what it says is, like the only important thing is that it says that when you have a derivative of vector with scalar, the output is a vector. The derivative of a scalar with a vector is again a vector. Like it just likes things to be vectors as long as you can make them. But in chain rule, etc., this kind of thing is not possible. So in chain rule, it will use numerator layout. So just be careful. So let's actually see where it's written, so that we can sort of get a feel of its notation. So it has a bunch of useful identities. One of them, like this one, is actually quite useful. This is called the Sylvester's identity, which basically says that if you have like a, and it's actually more general than this, he has given a more specific version of the identity. But what this is saying is that if you have like a huge matrix, if you have a huge matrix, U, V, transpose, so this is the outer product, this is going to be like, this is like 10,000 cross 1 and 1 cross 10,000, this is going to be a 10,000 cross 10,000 matrix, and then you are adding identity to it. And if you take the determinant of this, its determinant is going to be the same as the determinant of 1 plus V U transpose. Yeah, it doesn't matter U transpose V or V transpose U. It's going to be the same thing, right? So you are able to break it down. So this is just something that was useful to me once. That's why I'm pointing it out. But yeah, I mean, so here you can see that he specifies the layer.
We can count that determinant of I plus U.
Yeah.
How it is.
Oh, sure. I think the way to show this is that you can break this down into a product of two matrices. So here's how the proof goes. We know that a determinant of A into B is equal to determinant of A into determinant of B. We know this. And therefore determinant of AB equals to determinant of BA. And if we can specify I plus UB transpose as a multiplication of two matrices, therefore basically we can commute those matrices. So I'm forgetting exactly what the structure is, but I remember it's like a trick where you have like I here, U, and then maybe I think I, B, something like this. I'm forgetting exactly the thing. And if you commute, you're able to get like from this structure to this structure. And that's how the proof goes. But I can't remember right now. So like this is why this thing works. Yeah. And here you have like the same exercise that you did earlier as a formula, that derivative of x inverse equals to minus x inverse del x. These are outer products. I don't even know what this means. This is just the chain rule. This you can see quite easily because both the derivative and the trace are linear operators. Like therefore they commute. Like you can just push one inside the other without any problem. And these are all like coming from your calculus. And yeah. The reason I opened this page was just to show that he is using a mixed layout, and that is specified over here in these lines. That if you have a vector by vector, it's going to be numerator, otherwise it's going to be like always vector. That's what happens. Okay, and then after that, I also noted down two important things in the notes, which are two more formulas which are important, which might come useful, might be useful. Like I'm only focusing on the mechanics here because the intuition and SPD and PCA like Raman is gonna do, but it's just much easier to sort of handle the algebra and math separately so that you are not like you're able to follow along the derivation and you get the geometrical viewpoint of all the things. So we'll come to that also. So these are like the final two things that I talked about. Now, why is it that the trace comes here? Is the question. So first of all, like what is it even saying? So it's saying that U is some matrix. It's a 2 by 2 matrix. It's not a vector. And G is some function which acts on that G is some function which acts on that. And I think it's element wise. Oh, sorry. Yeah, I'm not very sure about it. I think I'll go back and post on Piazza what exactly this is trying to say. But this basically is, we are coming like almost to the end of the things that I've prepared, and after that we can go over like Raman's derivation from yesterday. If that's useful. So this is like basically the idea of a differential. So when you have a, like, forget about, even if you forget about matrices, let's say you have a scalar function, a single valued function, which is dependent on multiple variables. So you have your x is equal to f of y equal x1, x2, xn. The differential is basically what it's saying. So the differential is going to be sum of fx1 dot fx1 prime times dx sigma. Right? So the differential is an actual difference, like it's an actual quantity. This thing is how much the quantity would change when you change xi by that much. Right? So to actually get the total change, you have to sum up all of them, and then you get. So this actually shows how this is why you write down the gradient as a vector, and then when you multiply it, when you take dot product with the direction, you get the directional derivative. You get the change in that direction. That is because of this formula. That this formula can be written down as a vector multiplication, as a vector dot product, because this is just, this is exactly the same formula. So that gradient thing is actually like saying that when you multiply v with any direction, you will get the final change there will be in that direction, and that is why the gradient. So according to this, the gradient should be, so according to this, whenever you take, so the gradient's direction is something which is perpendicular to the direction of most change, it is it is parallel to the direction of most change that happens. Like if you have a gradient, you think of it as a vector, right? If you think of this as a vector, if you think of this as a direction,
the gradient is parallel to the exchange rate.
yeah, that's what I'm saying. So if you have this is your gradient, right? If the direction is parallel to this, the dot product is going to be the maximum, and you're going to have maximum change. And that is why we say that the gradient is parallel to the direction of the most change, right? So that's basically where it's coming from. And this thing, like the total change is the differential, and therefore now a matrix differential is just the total change with respect to all of its elements arranged in a matrix form. Like the actual, so it's always defined for a scalar on top. So it's always, usually it's always going to be a trace. And we'll come down to the actual formula later. First, let's just discuss why even this is being talked about. This is being talked about because he's assuming that f is some ax. So let's imagine that f equals to ax. Then what he has said here is that f prime x is the part that is linear in dx. So he writes fx plus dx and fx. So he says fx plus dx is equal to a of x plus dx. And when he subtracts them, he gets a dx. And then he is taking the trace of that. And the reason for that is because what is is special about the trace? So you see that this thing, f prime, so he talks about this as the Jacobian. So this is like the same thing we have talked about earlier. The reason I was trying to motivate was that this had like some special property basically. I'm forgetting what exactly that was. So what is the trace of ADX? It is it is exactly this sum. Right? You want to find out what will be the change in the total output that is linear with respect to x, and therefore you say that Ty is going to be the trace of ADX, and that is why traces always come along, and they usually come along. But that is in this differential form. There's also other algebra which we will, when we go over Roman's derivation, we'll see. Is this a bit, even a bit clear? Was that is the motivation clear? Or rather, tell me what are the problems that you're facing? It's probably not clear. What is unclear?
I guess personally, how ADX is equal to that sum.
Oh yeah, so ADX is not actually going to be equal to, so okay, let's write down ADX. It's going to be A11, A12, A1n, up to ANN. When you multiply with it, so you have dx1, dx2, dxn. It's not ADX which is going to be equal to the sum, it's the trace. So let's see what the trace is going to be. The trace is going to be this multiplied with this. A11, A1. So A11 D of x. So this one dot. A12 x2 dot. A1n xn dot plus A21. So the trace that you're saying, the trace is actually this sum, right? Is that clear? First of all, you actually multiply, and all right, because if you multiply this, you're going to get a vector. There is no definition of a trace here.
So in that matrix to the right, is that the partial derivative with respect to each element of the matrix? Or
so okay, so this is just A, and this matrix contains all the differentials. So like the small changes that you make in every entry of a matrix X.
So that's like dx11, dx12.
Yeah, exactly. Now when you multiply them and find the trace, you're basically taking the in the output, you are taking the diagonals. Like these things. So I basically, all of these are summations. I basically written them down. So the basic point is that this So this trace is going to have all of these components. And if you're trying, so what he said, so let's see what's like special about this. So it's basically saying that it's always going to have only one term. So A11 will multiply with X11 dot. I guess I can't really think of anything special about this other than like it's just the thing that he chose to take derivative of. But I mean, anyway, we can see that the derivative of this is going to be equal to A.
And,
yeah, okay. So wait. So at least we have written down what the trace is actually equal to. Like we have actually written down the numerator term as an explicit summation. Now all we have to do is see that y is this equal to x itself. And that's actually easy. Y is that equal to a itself. And that's actually easy to see because you can like actually read it off from here. Like just take derivative with respect to only this element and you will get a11. So basically this comes out to be equal to a. So the reason for doing it this way is because this is like another notation. This is the differential. So there's like the line between the differential and the derivative. And I just wanted to make it clear. So like this, here you see there are no derivates, there are no partial, there are no things.
so is the reason this is mixed notation that the a sub 1 is the row vector, and then dx sub 1 is the column vector?
Oh, this here is not, it's numerator, this is not mixed.
Okay.
Yeah. So, okay, so I'm sure this sort of left everyone confused, but I'm going to try and clear this up. The reason for bringing all of this is because this sort of form, like this form you can find in many places in the algebra. Here you see that there's a trace and you're taking, so it's basically saying that the differential of like the scalar valued function is equal to a, and this is just a formal way of proving that why we are collecting all those partial derivatives. And like these formulas get used in some cases basically. And I'm only giving just the math here of the equation and how it's going to apply. But I hope that this was clear that you can actually like a dx, you take, and then you take the trace, and then you write it down as this actual summation, and you will see that it comes out to be the same thing. Therefore, the differential of the trace of a is equal to a. Okay, let's come to SVD. So there was a theorem which so yeah, I went through like this Jacobian. Yeah, there were two more things, but I guess I can quickly state them. Does everyone know like this way of finding the derivative of a determinant? Has anyone ever come across this? That if this is like the determinant sign. Like these dots mean derivatives, and basically what I'm saying is if you're taking derivative of a determinant with respect to the entire matrix, you can split it into like taking just the derivative, like determinant of the derivative of the first row plus the determinant of the derivative of the second row plus so on and so forth. Like that you can split the determinant's derivative into this like linear sum of like taking derivative of each row separately. like, has anyone like come across this before, even as like a fact? Okay.
I think if each of the members are functions of X. What derivative do you take?
Oh yeah. So like if you have these are functions of some parameter. Yeah. Okay. Yeah. I should be more clear. Here, these are like functions of some parameter. So the motivation or the reason for this is kind of because of different characterization of determinants, like it's kind of messy. So like determinants are a n factorial sum of permutations of things. Like I'm probably not going to do justice to it, but like just remember. First, try to remember this identity, and I'll like give a more detailed reason later on. But in short, it's just because this is like a sum of certain terms, and the property of each of those terms is it's going to contain only one element from each row, and therefore when you take and it's going to be linear in those. So like if you take derivative with respect to any element with respect to t, you can apply chain rule on those terms separately. Like it's basically a application of the chain rule. That is, this derivative is a sum of certain terms, like it's, and every term is a multiplication of n elements from this matrix. And so, okay, in the A case, in the two-dimensional case, it's easy to see. It is A11 into A minus A1, A1. So it is the summation of these two terms. And when you take derivative, you can apply chain rule to each of these terms separately and then put them back together. And when you do that, when you apply chain rule to these terms and put them back together, this comes out to be the case. And there's also another identity which is called the Jacobi's formula for the determinant of the derivative. But I think like let's just get, if it is covered in the course. Yeah.
What are the superscripts for
These?
that and on the left-hand side?
Oh yeah, I just meant that these are like parameters of some. These are like functions of some parameter.
Sure.
And you're taking derivative with respect to that, right? These are like t's. I meant to say t. So this is a function. Okay, final 15 minutes. These things I've basically picked up. This again is from Wolof and Lohan. This is like a characterization of the SPD. Yesterday, Raman said that it's, you can think of the SPD as providing the best approximation to a rank K matrix in the Frobenius norm. And I was like, I thought it was the spectral norm, and it is also the spectral norm, and apparently it's also the Frobenius norm. But anyway, I don't think I would even have time to go over the proof. I'm not very comfortable explaining the proof right now. But let's see, like, what is the theorem even saying? Let's just first try to understand that, so that we will understand like what was Raman trying to say, basically. So this theorem is basically saying that SPD is a way to find out how close or how far away a matrix is from the space of some rank K matrices. So first of all, we will have a lot of terms. So rank. So what is a rank of a matrix? Does anyone know? let's say, and yeah, it's the, I mean, it's the number, like there is no really smallest, like if they are independent, like they are, you can't have non-maximal sets of.
Yeah, I think the definition we saw yesterday had an in it, so.
So this rank basically tells you how, like, that the columns are independent, and it turns out that independence in columns also means independence in rows, at least for square matrices. Oh, sorry, it's for everything. So the column rank of a matrix is equal to the row rank, which means that the number of independent columns in a matrix is equal to the number of independent rows in a matrix. That's like the thing. So what this theorem is saying is that you imagine the space of all matrices which have a certain rank. So imagine the space of all matrices which have rank 1, then spaces of matrices which have rank 2, then rank 3, rank 4. These are disjoint spaces, right? Like, I think, except, like, I'm not too sure about whether 0 fits in any of them, like what happens to the special case of 0, but disregarding 0, everything else is going to be, like, either a matrix is going